Electric motors are responsible for over 90% of all motion in modern factories. Without them, entire systems would come to a halt. Yet most of us have never actually seen one in operation, not even once. Building a motor like this is far from simple. Thin sheets of electrical steel are stacked with tolerances of just a few hundredths of a millimeter to form the magnetic core. Copper wires are wound precisely according to calculated patterns, ensuring every turn carries the correct voltage. Then come the rotor shaft, bearings, and cooling system, all working together with the precision of a living system. In this video, we'll follow the complete journey, from raw materials to a fully assembled motor, placed on the test bench and ready to deliver motion to every corner of a modern industrial world. Electric motors aren't just the foundation of modern engineering. They're the silent force powering nearly every sector of the global economy. Each year, the world produces hundreds of millions of these machines, from tiny motors tucked inside vacuum cleaners and electric fans, to massive industrial units driving mining operations, steel production, and renewable energy systems. The global electric motor market has already surpassed $150 billion, and it's still growing steadily, fueled by two powerful trends: automation and the shift toward cleaner energy. Which industry do you think would be hit hardest if electric motors suddenly disappeared? What's truly remarkable is how elegantly these machines work. When electricity flows through the stator coils, it generates a rotating magnetic field. This field induces current in the rotor, setting the shaft into motion. That simple act of rotation, smooth, continuous, forms the core of everything from automobile assembly lines to the air conditioner cooling your home right now. To create rotational motion inside an electric motor, the first thing that must be built is the stator core, a metal structure with special magnetic properties acting as the guiding frame for the entire magnetic field. From the outside, it may look like a simple ring of steel, but crafting a uniform block with microscopic precision demands an entire production line operating under exceptionally tight control. It all begins with stamping thousands of laminated steel sheets, each just a few hundredths of a millimeter thick. A thin insulating layer coats every sheet to reduce energy loss caused by eddy currents within the core. These aren't just circular discs. Each one is intricately shaped with fine grooves. That's where the copper windings will eventually sit. To ensure every groove lines up perfectly, the sheets are stacked using a high-precision alignment system with near zero tolerance for error. Instead of using heat, which could distort the material, manufacturers rely on high-pressure presses to compact the stack into a solid cylinder. This method preserves both the geometry and the magnetic properties of the core almost entirely intact. Immediately afterward, every groove is lined with ultra-thin insulation, often made of polyester or high-performance materials like Nomex. These insulating barriers prevent direct contact between the copper wires and the steel, ensuring full electrical isolation. The entire process is performed by robots. Even a misalignment of just a few hundredths of a millimeter could lead to a short circuit the moment the motor starts. Here, in this hidden core, the motor's efficiency begins to take shape, from magnetic conductivity and voltage control to rotational stability. A seemingly modest component, yet it forms the foundation of every motion that follows. Once the stator core has been precisely formed and secured, the next step begins to breathe life into the motor: copper winding. This is the moment when electrical pathways are established, forming the bridge between raw electricity and mechanical motion. Before any copper wire is inserted, each groove in the stator must be lined with a specialized insulating material. Typically, it's a synthetic fiber paper that can withstand high temperatures and does not conduct electricity. This thin insulation acts like a protective cushion, preventing any electrical leakage into the steel core beneath. Thanks to this layer, the copper windings can sit precisely where they belong, fully isolated from the metal structure below. Then comes the enamel-coated copper wire, fed into place by high-speed winding machines. But speed isn't the real challenge here. What truly defines the quality of the windings is how each loop is arranged. The wire must lie flat in the groove, no twists, no overlaps, and always held under consistent tension. To achieve this, automated systems scan and identify every slot beforehand, calibrating the winding pattern and insertion depth with pinpoint accuracy. In large industrial motors, each slot might hold dozens of wire loops, and every turn must be laid in clean, ordered layers. Once winding is complete, the coil ends are temporarily secured. Only when the copper is locked into position with geometric precision can the motor safely conduct current, ensuring every pulse flows in the right direction and every movement that follows unfolds with smooth, programmed precision. Once the copper windings are in place and temporarily secured within the stator core, a critical stage begins: insulation and thermal processing. This step ensures that the entire wiring system will operate safely and reliably over the motor's lifetime, no matter the temperature, pressure, or humidity it encounters. During operation, current constantly flows through the copper coils, generating internal heat. If not properly secured and protected, these wires can vibrate, shift out of place, or even spark at contact points, especially in high temperature or high vibration environments. To prevent this, every strand and crossover is carefully addressed by hand or with semi-automated tools. Workers use specialized technical thread, thin, strong, and heat-resistant, to tie down each bundle of wire according to the motor's design, applying just enough tension to hold everything firmly without distorting the core. Next, the entire stator assembly is immersed in a bath of liquid insulating resin, typically a specialized epoxy or polyester. Using vacuum impregnation or electromagnetic dipping, the resin is drawn deep into every gap between the wires. Once cured, this coating forms a solid, waterproof, and fully insulated mass that locks the windings in place, a sealed structure built to endure the harshest industrial environments for years to come. Once the stator has been fully insulated and structurally stabilized, the production process shifts to the motor's remaining core, building the rotor. This is the part that spins, brought to life by the magnetic field generated in the stator. And to do that efficiently, it requires a robust magnetic structure of its own. Thin, high-grade electrical steel laminations, each coated with insulation, are carefully fed into a precision press. Every sheet is aligned and stacked with exact orientation, forming a cylindrical body with narrow slots running along its outer edge. Once the required height is reached, the entire stack is compressed under high pressure using a hydraulic press, locking the laminations into a single rigid core. This solid rotor backbone will soon become the heart of motion, the spinning center around which the motor will come alive. Even after being compressed into a solid mass, the rotor core can't spin, not yet. To become a complete drive unit, it must be mounted onto a central steel shaft, the component that transfers torque from the motor to the machinery it powers. This shaft is forged from high-strength alloy steel, often harder than the steel used in the magnetic core itself, to withstand continuous mechanical loads during operation. The machining process begins with cutting raw cylindrical stock, which is then fed into a CNC lathe for precision shaping. Each step-down surface, locking groove, and bearing seat is formed by programmed cutting tools, following an exact blueprint. Every cut must meet extremely tight tolerances to ensure the shaft's dimensional accuracy. But size isn't enough. The shaft's surface must also be smooth enough to prevent bearing wear over time. After machining, it undergoes detailed inspections for concentricity and runout. Only when it passes every technical benchmark is the shaft deemed ready, prepared to be paired with the rotor and begin its role as the spine of the entire system. Once both the shaft and rotor core have been machined to precise specifications, the next step is to fuse them into a single, unified structure. The shaft is gently heated to allow slight thermal expansion, while the steel core remains at room temperature. Under the force of a hydraulic press, the shaft is driven deep into the center of the rotor, all without distorting either component. As the shaft cools, it contracts and locks firmly into place, forming a tight mechanical bond that requires no adhesives or bolts. This careful interplay of heat, material properties, and applied pressure creates a stable assembly, one capable of spinning at high speeds while maintaining the balance and precision essential for smooth, continuous operation. For the rotor to spin smoothly inside the stator, one small but vital component must be added: the bearing. This part reduces friction, stabilizes rotation, and significantly extends the motor's lifespan. Once the shaft is firmly secured within the rotor core, technicians press bearings onto both ends of the shaft using a hydraulic press. Before installation, the bearings are gently heated to expand slightly, while the shaft is kept at ambient temperature. As the bearing cools, it contracts tightly around the shaft, forming a solid interference fit that requires no screws or adhesives. No electric motor is complete without its outer shell, the protective armor that safeguards everything inside. The process begins with flat steel sheets, which are bent into precise cylindrical shapes. These blanks are then hot pressed in an extrusion machine, where two massive steel dies form the motor housing's basic structure. Next comes the welding of cooling fins, raised ridges that not only enhance heat dissipation, but also give the motor its rugged industrial appearance. Every welded surface is manually inspected to eliminate sharp edges or imperfections. Finally, the entire housing is coated with electrostatic paint, providing corrosion resistance and heat durability, a finish built to endure the harshest conditions. With the stator fully insulated, the rotor precisely fitted with its shaft and bearings installed in their exact positions, the motor reaches its final stage, complete assembly, where the stationary and rotating parts are brought together as one. Each sub-assembly is carefully inserted into the motor housing using mechanical centering tools that ensure the rotor shaft sits perfectly aligned within the stator core. The gap between them is minimal, just enough to allow free rotation without touching the magnetic core or inner casing. Assembly isn't just about putting pieces together. Every contact surface is inspected for flatness and alignment. Each bearing is pressed to the precise depth. Even the slightest geometric deviation, as small as 1/100th of a millimeter, can result in vibration, overheating, or a drop in electrical efficiency. Once the mechanical assembly is complete, attention turns to the electrical system. The copper wire leads from the stator coils are drawn out from the motor cavity, ready for phase alignment and terminal connections. Using specialized testing equipment, technicians identify the correct phase sequence. Each wire end is then sleeved with heat-resistant insulation and securely crimped with cable lugs. The entire wiring bundle is neatly arranged and anchored to the terminal box inside the motor body, preventing movement or vibration during operation. The main power cable is fed through a protective conduit and routed outside the housing, ready to be connected to the power supply. This is the final step before the motor undergoes electrical testing and operational trials. Even with all internal components in place, the motor still requires one final stage before it's ready for real-world operation. The outer casing is sent into a specialized spray booth where the protective coating is precisely controlled for thickness, adhesion, and corrosion resistance, shielding the unit against harsh environmental conditions. Next, technicians install a thin metal guard at the rear, designed to prevent accidental contact with moving parts during operation. The terminal box is sealed with a rubber gasket, blocking out moisture and dust from entering the electrical system. Finally, the motor receives its identity. A specification label, QR code, and serial markings are affixed to the surface, serving as its passport, documenting technical details and manufacturing origin. Before leaving the factory to power thousands of hours of real-world operation, each motor must pass a final series of tests, confirming its full mechanical and electrical integrity. The unit is mounted onto a dedicated test bench, where an array of sensors monitors key performance indicators such as noise level, vibration, and no-load energy consumption. Current is supplied to the stator, the rotor begins to spin, and every data point is tracked in real time. Once dynamic testing is complete, technicians conduct a final round of manual inspections. They check the smoothness of shaft rotation, the stability of electrical terminals, and re-verify the accuracy of the identification label. Every component must meet exacting standards. Only after successfully passing this comprehensive quality audit is the motor cleared for packaging, ready to ship to factories around the world. From delicate strands of copper to relentless rotational force, the electric motor is a testament to how humanity transforms invisible currents into precise, enduring motion. Behind every unit lies a complex engineering journey, one that demands extraordinary precision in even the smallest of details. If you found this process as fascinating as we did, don't forget to leave a like, share this video, drop your thoughts in the comments, and subscribe to our channel.